Now, in this lesson, we have primary questions that need to be answered. The first one, which we have to answer, is what is the relationship between a function and its inverse, both mechanically and graphically? Okay, and number two, what is an inverse function? So, what is an inverse function? Okay. What else? Is an inverse function always a function? Is it always a function? Now, if the inverse of a function is also a function, how do we describe the original graph? Okay, next is how do we sketch inverse relationships? How do we graph inverse relationships using a grapher calculator in this case? And what happens when we take the composite of a function and its inverse? What is f to the negative 1? It's a notation, okay, for inverse function. F to the negative 1 of f of x is equal to what? Or what is also f of negative 1 of x? So all of these questions will be answered on this lesson. So what is the inverse of a function numerically? Now you are, for example, we have a shift, okay? We have a crew, and they have a shift from 0 to 8 hours, or for 8 hours to construct, okay, a road, or to repair a certain road by painting, okay? So suppose that there is a function d in there, or there is a distance, okay, involved. Suppose we have the crew, and we are going to describe the relationship between the time, a certain time, when the crew works on the shift from 0 to 8, and a distance within which from the beginning where the crew has ended from time equals 0 to a certain time which is equal to after 8 hours. So that's from 0 to 8 hours. Now suppose our d, okay, is a function of time. So that we're going to define d as a function of our time, where our d is in miles, the distance that the crew has traveled or has worked on for a certain time, and t is in hours. So that is our original function. D is equal to f of t. Now suppose this table describes suppose this table describes the work that is going on for the crew to paint the certain work which is called painting the center stripe is denoted by this table. So at t is equal to 1, the crew has already painted the center stripe within a distance of 0.2 miles At t equals 2 hours, 0.6, 3 hours, 1 mile, 4 hours, 1.4, 5 hours, 1.8, 6 hours, 2.2, 7 hours, 2.6, and lastly, after 8 hours, we have 3 miles. Now this tabulation is actually a computation which is based on assertions that there were already previous shift crews, okay, working on the same center stripe in the past. So from then on, we constructed this table, okay, because we already know, we could predict how many hours and how long would the center stripe be painted over to a certain course, a certain shift of 8 hours. So this is D is equal to f of t. Okay, you can see that our f of 1, which is D is equal to f of t, this is our f of t. Okay, that's f of t. So at f of 1, which is this one, this is equal to t is equal to 1. So our f of 1 will be equal to 0.2. T is equal to 2, our f of 2 is equal to 0.6, and so on and so on. Now, as long as the crew does not stop painting during the 8-hour shift, the number of hours it has been painting is a function of the distance. So remember, if the crew does not stop painting, okay, let us take the reverse picture in view. As long as the crew paints non-stop during the 8-hour shift, then we could express t also as a function of the distance. So let's do that here. If the crew does the work non-stop, we have a picture which is D, or okay, somehow related to t inversely, so our t now, let's say it's a function of our t, or let's take another variable for our function. So let's say this is g of d. Then we will have this inverse picture in here. Okay, so this would be our new table. We have the distance, which is in mile, which is a function of t, which is in hours. So as you see, now in reality, okay, in reality, let us set aside a reality for a while. Let us say this t and d are related by means of, they are inversely related. And let's take out the real world, for example. Okay? So this would be, the thing that you see here would be our t, which is a function of our distance, which is in miles. So as you can see, this one is the inverse now. So if this is our inverse, okay, then we have our f negative 1 of 1. This 2 here will be our f of negative 1 of 2, or it should be the opposite, okay? F negative 1 of 0.2. And this is f negative 1 of 0.6. This is f negative 1 of 1.0, and so on and so forth. So what did we do here? We assumed that the distance d in miles in a particular highway crew paints in an 8-hour shift is given numerically by this function of t in hours had been on the job, and we also took the inverse relation of that one, which is our t now would be a function of our distance. In this case, we call this one our input. Where is our input? This side is our input. Okay, this part is our input. This side, it should be, okay, it should be closing inside the box. Anyway, so this one here is our input for this side, and this is our output. So that's our output. Okay. Now in this case, on the other side, on the right side, we have our output here, and this is our input. Okay, and as you notice, okay, these two tables here, they are presenting a somewhat distinctive characteristic or equality, which is, as you notice, okay, they are inverses of each other. So f of t and g of d are inverses of each other. Look how they are inverses of each other. We have the input, which is the output of the other. The input here is the output here. And the output here is the input here. They are inverses of each other. And furthermore, we could say that the values have been interchanged. And basically, the inputs and outputs have been interchanged. So that's what an inverse of a function numerically using numbers mean. Now let's go to defining them in terms of graphical interpretations. So going back from these tables, okay, from these tables, this is the table that you see is the table for the original function, d as a function of time. You know, the distance painted by this crew on that particular shift of 8 hours has been defined by this distance from t is equal to 1, our f of 1, which is our d is equal to 0.2 miles, 0.2 mile, and so on and so forth. Now this is our graph for this table. Okay, so for this table, the corresponding graph is to its right, which, as you can see, we have the points there appearing, which correspond to our pair of points for the t and d for the particular shift. If our t is equal to 1 hour, then we have 0.2 miles corresponding here to the point here. Now on the second portion, when we take the inverse of our, when we take the inverse for the time and distance, where the crew does not stop painting, they painted non-stop during their shift from 1 to 8 hours, then we could take d, which is the distance, as a function of our time, which is, in this case, this is g of x. And as we explained in the previous slide, that this is the inverse of the original function, the one appearing here on top. So this is the graph for this table. Okay, notice the shifting. For the top graph, the graph on top, you could see the shifting to its the graph shifted from landing on the t-axis. Now it's on the or on the still on the t-axis, but t-axis now is on the vertical side. This is our t now. We're in this is our t in the original, and our d on the original function is on the vertical axis, denoting that is dependent rather on t. But now our t is dependent on d. So if we take both of the graph, okay, if we take them both of them, then we will have another graph which is a combination of the two, and we drew the line y is equal to x, which is the primary functional linear, which is on the middle, cutting our y and x axis into two. Now we can see a reflection for our f, which is this case. Okay, this is our f, and this is our f of -1. This is our f of x or f of t, and this is our g of d. And we can see that they are reflections of each other by looking at the mirror through y is equal to x. This is our guiding, function, our guiding linear function. It's supposed to be a straight line. So let's do it with a okay. Let's do it with a more okay. With a more accurate, okay, let's do it this way. Okay, so this is our guiding line, the one in the middle. So as you can see, our f of t is a reflection. This f of t here is a reflection of our g of d. They look similarly the same, just that this one, the f of -1 is twisted, landing on the y-axis, and now our f of t is landed on the x-axis. And notice also that the domain for our f of t is, which is equal to from somewhere here, okay, from here to 8, and our range is from 0 to 3. And in this case, our g of d has a domain from 0 to 3, but a range of 0 to 8. So that's somewhat, a reflection. So they are reflections of each other.